determine the value of the resistance R that causes the voltage measured by the voltmeter in circuit to be shown. All right, so something a lot of students they mess up. They have to understand. Honestly, if you do this, let me see if I have a white. Does it have white? No, it doesn't have white. Whatever. If you do this, you'll be better off. If you literally erase this, you'll be fine. Those are two separate circuits, and they draw it like that, and it's confusing, but those are two separate circuits. So you can literally disconnect them. What they've done is they tried to show you that all of this line is grounded. But if you put the ground right here, and you put the ground right here, there's nothing different. You can literally draw them as two separate circuits. Does that make some sense?
Mm-hmm.
A lot of students think, and I used to think so too, a lot of students think that current's going to go up through the line and then come back. Current cannot go backward and forward in the same line. Current has to go one way in one line, and that's it. And so if you realize that current can't return, then just erase that line. Erase it. So I'm going to erase it. Now, when I erase it, I make the problem a lot easier. Honestly, I make it really, really easy. So this guy is going to create the conditions for him to work. How do I know that? Because this is where my IA is, and this is where IA is. Make some sense?
Mm-hmm. So
the first thing I'm going to do is I'm going to solve this circuit right here, and that circuit is a current divider. So that's really easy. So I'm going to say IA. It's going to be negative. IA equals negative, and it's going to be 3 times 40 divided by 50, which is 120 over 50, which is 12 over 5. And that's going to be amps. All right, so it's going to be negative because this guy's pointing downward, but this guy's pointing to the left, and they're backwards to each other. So I know it's going to be negative. Make some sense?
Mm-hmm.
All right, so I know that's negative. I plug this number into that guy right there. And so what I'll do is I'll put that a little bit cleaner. Come on. Oh, my computer's doing that thing again. All right. Where it can't keep up. I figured out what's wrong. It's when I plug it into my into the wall, it starts to do a lot of stuff at once. But I'm going to plug that in there. Now, mind you, now I know that's 12 over 5. So it's 5 times 12 over 5. And look how easy that works out. What I want to show you is this. It's a voltage source. And so a lot of students get messed up. This is a voltage source. So the number that we're going to get is going to be a voltage now, not a current. So it's 5, and then we had 12 over 5, right? That cancels. So what this really is 12 volts. That's 12 volts sitting there. Make some sense? It's not 12 amps.
Mm-hmm.
It's a voltage source that's dependent on a current. And that is the trickiest thing that's probably the trickiest thing that they can show you. I mess up students with that all the time. And even still, in the book, if you look, there's a couple problems in the book where I do the same exact thing trying to trick the students. And I walk the students through it, say, look, it depends on the current source, but it's still a voltage source. And you got to be very, very careful with that, okay?
Yeah, so basically, I just look at it like diamonds are voltage sources and circles are current sources.
No, that's wrong.
No, or arrows.
That's wrong.
It's like the arrows too. No?
You have independent sources. Independent sources look like this. This is a current. This is a voltage. Dependent sources.
I mean, well, yeah, that one makes sense. When I say diamonds, I'm specifically only talking about dependent sources. Oh wait, both of them. Yeah, wow. Okay.
They have dependent current sources. They have those.
So
that's the
really
thing.
Just pay attention. If it has an arrow, it's a current source. If it has a plus and minus, it's a voltage.
Exactly. That's all you got to look at.
Okay.
And so now we're focused on this circuit right here. Now that we know the voltage. Now that you know the voltage, it doesn't matter if it's a dependent source or not. It's still a source. And so you're going to treat it like a source. You got to know that a voltmeter doesn't really matter. The voltmeter is just measuring the voltage. So what happens is a lot of students look at this and they go, oh, that's a part of the circuit. I got to plug. No, you don't. It's a voltmeter. Its job is to not add resistance. Its job is to just measure voltage. So I'm literally going to forget the fact that this bad boy is here. All right, forget it. I wish I could erase it, but I can't erase it. And I don't have a white pen. So it's going to take too long for me to try to scratch all of that out. So basically what we really need to do is find this voltage right here, the plus and the minus. because they said that the voltmeter has to measure 6 volts. You see that?
Mm-hmm.
So we know that this is 6. We know it's 6 because they told us V equals 6. So once you get good enough, you'll recognize that this whole circuit is a voltage divider. Once you like get rid of all of this stuff, like I was saying, once you forget about that, you'll see, oh, this is just a voltage divider. You'll be fine. And then from there, you say, okay, I just set up my voltage divider equation, and everything will be just fine. If I set up my voltage divider, it's going to be 6 equals 12 times R divided by 18 plus R. 18 times 6 is 60 plus 8 times 6 is what? 48. So that's 108 plus 6R equals 12R. 108 equals 6R. 108 divided by 6. God knows what that is. That's a calculator moment. Oh, hold on. 6 divided by 6. 18. Boom. R equals 18. And that's how you figure that out. Make some sense?
Mm-hmm.
Now, I flew through that. I'm not going to lie. I kind of just like ran through it. But at this point, I do understand that you are able to kind of like follow me on the steps. And I know that you can probably like recreate it. Because at the end of the day, watching me solve circuits is nice. But you will never get good at circuits if you don't solve them. Never.
Mm-hmm. Okay.
Never.
So the quick question I have, right? So like then let's say if this negative right here was grounded, that negative terminal, let's say that was grounded, right? It's no longer a voltage divider.
It is.
This part right
I
here.
grounded it.
So you
look. Oh, so that's grounded. That is grounded. And so what I can do is you can recognize the ground does not mean you have to do voltage no voltage method. It doesn't mean that. Ground is actually supposed to be in every circuit, to be honest with you. Every circuit's supposed to have a ground, to be real with you, because every circuit in real life has a ground. And so you start to see it in electronics. You'll see them, they're going to draw the circuits completely different in electronics, and it's going to ruin a lot of students. That's a whole different story. But you're supposed to, honestly, in every circuit you get, it would be ideal if you put a ground somewhere, because that makes the most sense. Because at the end of the day, in all of the real life circuits, there's always a ground line. So just because I put this ground here doesn't mean I have to do no voltage method. I can do no voltage method. If I did do no voltage method, I would name this A, and I would name this B, and I would just say VA equals 12 because I already solved for it. Then I would set up my equation. I would assume that the current goes like this. I'd assume that the current goes down. I'm sorry. Down. And oh shoot, it's supposed to be negative. Hold on, I'm messing up.
So I get everything you're saying, but what I'm saying is that so you did do the voltage divider. So really, the whole ground thing doesn't really apply when you're doing the voltage divider principle itself.
No, it doesn't.
Okay,
it doesn't.
Okay, that's what I was trying to figure out.
The ground is just nice to have on a circuit, but a ground will not affect the fact that you have a voltage divider. It won't affect anything. Having a ground does not affect which method you use. Having ground is, you need a ground to do the no voltage method. You need a ground to do no voltage method. That's it. But if you have a ground, you don't necessarily have to do no voltage method. Okay. And so that's literally how that works. And this will solve out to say VB equals whatever that'll be. It'll be 18. But yeah, man. Yeah.
Okay.
This will be R. Oh, I messed you up. It'll be VB and R. VB, and then I know VA minus VB or VB minus VA equals 6. There we go. So VB has to be 18 and this will be divided by R, and then it'll solve to give you R equals 18. That's what it actually is supposed to do. So this on the left is solving it with voltage divider, which was easy. On the right was solving it with no voltage method, which was also still decently easy. So this is one of those examples where you can start to finally see how solving it in different methods, it really becomes a matter of preference. And you will only develop a preference as you practice.